right, in the notes today, we're going to talk about a particle detector, and I wanted you to see this picture because this is what you would see inside of a particle detector. So a charged particle, maybe coming from space, comes flying into the detector, and what you have is something in here that allows you to see the path of the particle, and you put a magnetic field in here, and because a charged particle will feel a force, it's going to take this curved path. So that's what we're going to be talking about. So if you go to the notes, you're going to be here. All right. And it talks about this, that a particle detector uses magnetic fields to determine the charge and mass of a particle. We have a diagram of it below. So my charged particle will come in this way, and the magnetic field is into the page. And it says here that it's an alpha particle, and I need to define that. So I'm going to do that over here, maybe an alpha particle is basically 2 protons and 2 neutrons. All right, so we're going to have to find the mass of the alpha particle and its charge. So the mass is going to be 2 times the mass of a proton plus 2 times the mass of a neutron, which is going to be 2 times 1.67 times 10 to the minus 27th plus 2 times 1.67 times 10 to the minus 27th. And when I find that all together, I get a mass of 6.68 times 10 to the minus 27th kilograms. So there's my mass. And the charge, I only have to worry about the protons per the charge. So it's 2 times the charge on a proton. And we should remember that the charge on a proton is 1.6 times 10 to the minus 19th coulombs. So that's going to be 3.2 times 10 to the minus 19th coulombs for the charge. Now in part 1 here, it says what will be the shape that it takes. Maybe we'll talk about that up here. And I'm going to use the right-hand rule for this. And this thing is positive, so I just use my right-hand rule. The charge is moving to the right, and the magnetic field is into the page. So I make my thumb point to the right, my fingers point into the page, and my palm is pushing up. So the force on it is going to be up. So it starts to curve like this. Now when it's at this position, it's going to change. I'm going to do the right-hand rule again. The charge is moving up. The magnetic field is into the page. So my thumb points up, my fingers point into the page, and my palm is pushing to the right. So it's going to make it go this way. And it turns out it makes a circle. And we figure that out by the right-hand rule. So remember I said that we can use this to find the charge. If it was a negative, negatives go the opposite way. A negative would actually curl back around this way. And then part 2, we want to find the radius of curvature for this circle. So we're going to start out by using this to find the force on the particle. And I'm not worried about the sine theta because everything's at right angles here. I'm moving this way, and the magnetic field is into the page, so they're at right angles. So I can just use QVB and ignore the sine theta. The Q we found over here, 3.2 times 10 to the minus 19th. We have V right here, 6 times 10 to the 5th. And we have B, the magnetic field here is 2. So when I multiply that all out, I get force equals 3.84 times 10 to the minus 13th newtons. So there's the force. Then we have to use our knowledge from the first semester of circles. And remember, when we have circles, we replace F net equals MA. For anything going in a circle, A becomes V squared over R. So F net is MV squared over R. So I'm going to put the F in over here, 3.84 times 10 to the minus 13th. We got the mass up here, 6.68 times 10 to the minus 27th. The V is here, 6 times 10 to the 5th. Okay, remember to square that and divide it by r. When we solve that, we'll get an r of 0.00626 meters. So this is really just a continuation of using this equation to find the force, using the right-hand rule to find direction. And then we're just going to add in that we have to do F net equals ma, and since it's a circle, replace the a with b squared over r.